going to talk about today? I'm going to talk about intermolecular forces. This is one of the topics that you gotta know as you move on to other chemistry classes. Now I have a question for you. Okay, here is my question. How many water molecules are in this bottle right now? So how many water molecules are in this bottle right now? What do you think? I know I can't hear you, but if there's anyone in the room right now, tell them, how many water molecules do you think are in this bottle right now? 10, 20, 100, 200, how many? What do you think? There are probably millions of water molecules in here right now. So there are millions of water molecules in here right now. Now, the question is, hopefully you were close to that number. The question is, if there are millions of water molecules in here right now, how are they held together and they're not running away from each other? So we have millions of water molecules in here and they're nicely held together and they're not running away from each other. Why is that? The reason is because intermolecular forces. So intermolecular forces, those are forces that keep the liquid and the solid together. So intermolecular forces, which we also call it IMF, we call it IMF. Those are forces that they keep solid and liquid together. An example is here, in this bottle, I have millions of water molecules, but they're not running away from each other. They're nicely held together because they're held together through intermolecular forces. Now, I put in a little picture here. So let's say these are water molecules that are held together very nicely, okay? And they're held together through intermolecular forces. Now, what happens if I heat up water? This is the symbol for heat. What happens if I heat up water? What happens? You've done it before. When you have water and you heat up water, what happens? The liquid goes to gas. Now, what happens when you heat up water? When you heat up water, what you are breaking the intermolecular forces between the water molecule. You're not breaking any bonds. You are not breaking any covalent bonds. The covalent bonds between the water molecule, the covalent bond of water molecule, let me show you what I mean by that. So here the Lewis structure. Oh yeah, you're gonna remember your Chem 1A. Here's the Lewis structure. The covalent bond, you're not breaking these. These you cannot break. These are strong. You're not breaking any covalent bond. But when you heat up water, you are breaking the forces between the water molecule. You are breaking the intermolecular forces that are holding the water molecules together so that it can go to the gas phase. So far, so good. Okay. So intermolecular forces is the attraction that keeps the liquid and the solid together. So IMF is the attraction that keeps the liquid and the solid together. So far, so good. Okay, so now that you hopefully know what IMF is an attraction that keeps solid and liquid together, we're gonna go over what are the different types of IMF. So what type of IMF is holding these water molecules together? So now we're gonna go over the types of IMF, okay? So we have five different types of IMF. And I'm going to list them from the strongest one to the weakest one. Actually, there are four. The fifth one I'm going to go later. I'm not going to put on this list. The first one is ionic. So these are the types of intermolecular forces. The second one is hydrogen bonding. Then is dipole. We also call it deep. And the last one is London dispersion, which we call it LD. That sounds cool, right? Alright, so these are the types of intermolecular forces. Now, I will go over each one with you today to make sure you understand what they are and how you would know what type of intermolecular forces a liquid or a solid have. Now, before we do that, what I want you to really understand is, why do we care about this? Why do you care about intermolecular forces? Now, here's why we care about intermolecular forces. Let me give you an example. Why we care about intermolecular forces. Water has a boiling point of 100 degrees. CH3Cl has a boiling point of 61.2 degrees. NaCl has a boiling point of 1413 degrees. So these are the boiling points, okay? So now the question is, why do we care about intermolecular forces? Here's why we care about intermolecular forces. When you look over there, NaCl has the highest boiling point. And then water is also pretty high. And then CH3Cl is after that. Now, here's why you have to care about intermolecular forces. Because intermolecular forces, they determine physical properties. Intermolecular forces, they determine physical property, right? So NaCl has the highest boiling point. Now, why do you think it has the highest boiling point? Because it has the ionic intermolecular forces. So if you have a stronger intermolecular forces, they're holding on together very tightly. So it's you're going to require more energy to break them up. So it has a high boiling point. Water, and I'm going to go over all of this in a second. Water has hydrogen bonding as IMF. It's the second highest one. So water has a high boiling point also. So why do we have to care about intermolecular forces? You have to care about intermolecular forces because they will determine physical properties. So intermolecular forces, they will determine physical properties. And by physical properties, I mean boiling point, freezing point, viscosity, vapor pressure. Those are all physical properties that are determined by intermolecular forces. So if you know the intermolecular forces, you can guess and you can predict, you can estimate what are the physical properties without actually measuring them, right? Without knowing them, you can go, oh, this probably has a high IMF, so it would have a high boiling point. So it would determine physical properties. And you can also predict that using IMF. You can predict physical property using IMF. All right, so now what I promised you is that one by one, we are going to go over the intermolecular forces. What's the first one on your list? Look at your list right now. What's the first one on your list? The first one on your list is ionic. The first one on your list is ionic. Okay, so you have an ionic intermolecular forces when you have ionic molecules. And if you remember from ionic molecules is an attraction of plus minus charges, right? Ionic molecule is an attraction of charged atoms, right? So ionic is an attraction of charged atoms. So every time you have an ionic compound, what's gonna hold all those together is ionic IMF. Now here's, before we keep going, I know you know this, but just to make sure, how do you know you have an ionic compound? How do you know you have an ionic compound? You know you have an ionic compound when you have a metal and you have a non-metal. So you know you have an ionic compound when you have a metal and you have a non-metal. So you have a metal, non-metal, you have an ionic compound, and ionic forces is responsible for that. Now, here's a question for you. Let's say you grab a bag of salt, okay? What is salt? NaCl, right? So you grab a bag of salt, is NaCl, and NaCl is an ionic compound because you have a metal and a non-metal together. Now, when you grab a bag of salt, you don't just have one or two salt in it. Those are millions and millions of NaCl molecules held together, right? So if I have a small bag of salt, again, it's not just a few salt molecules together. I have millions and millions of NaCl molecules held together. Now, how are they held together? Through ionic interaction. And I'm going to show you that. So millions of NaCl molecules are held together through ionic interaction. And ionic interaction has to do with plus minuses. It's a charge attraction. So if I have millions and millions of NaCl, how are they held together? Those molecules are held together through ionic interaction. Those molecules are held together through ionic interaction. And what is ionic interaction? It's just attraction of plus minus charges. So again, you have a bag of salt. Next time you have a bag of, you see salt, you go, oh, there are millions and millions of molecules in here. How are they all held together? Through plus minus attraction. Through plus minus attraction, they are held together. Sounds good? Okay. So that was our first one, ionic interaction. Ionic interaction is for ionic molecules, and what it is the attraction of plus minus charges. Is the attraction of plus minus charges. Beautiful. Hopefully you got this down. Okay, look at the list. I know I can't see you, but I can't hear you, but do this anyway. Tell me what is the next one on the list. Ionic is the first one. The second one is hydrogen bonding. Do you guys want to be cool? If you want to be cool chemists, they also call it H bonding. It just sounds really cool. If you're a chemist, you know, it would sound cool. So hydrogen bonding. Now, I make this joke, and it's a joke, but at the same time, there's a little bit truth to it too, that every time you take in an exam and you don't know what the answer is, and if hydrogen bonding is one of the options, pick that and you're probably right. But that's just a joke. Don't do that. Actually read the question and know the answer. So hydrogen bonding is responsible for a lot of things in our life. I have a question for you. What makes you unique? What makes you you? What makes you unique? What makes us unique, my biology people, is the DNA, right? We all have different DNA, and DNA, what makes you you? What makes you to be a unique individual? Now, as you know, DNA is double helix. Oh boy, I gotta draw this out. My biology friends are not gonna be happy about me drawing this out. Make sure. Okay, so DNA is double helix. So this is a DNA, and DNA is double helix. Now, what holds the two strands of DNA together? What do you think? What holds the two strands of DNA together? Hydrogen bonding. So hydrogen bonding is responsible for holding the strands of DNA together. Okay, so hydrogen bonding technically is responsible for you being you. Now, Titanic. Why did Titanic happen? Hydrogen bonding. True story. Now, if you remember, Titanic happened because the ship ran into an iceberg, right? Now, here's why hydrogen bonding was responsible for that. I'm making hydrogen bonding sound like a bad thing right now. So here's why. Ice is less dense than water liquid. Have you ever thought about that? When you put ice in a glass of water, the ice is floating on top. It's not going down. So ice, water solid, is less dense than water liquid. In most cases, in a solid form, things are more dense than a liquid form. But for ice, for water, water solid is less dense than water liquid. Now, why is that? That has to do with hydrogen bonding. So next time when you add ice to a glass of water and then the solid is floating on top, what are you going to be thinking about? It's like, hydrogen bonding is responsible for it. And I'll show you exactly why that is. I will show you exactly why it is in a little bit. But what I want to show you now is what is hydrogen bonding, okay? Let's go over exactly what is this hydrogen bonding. So, write this down, and I will go over this in a second. X and Y could be nitrogen, oxygen, or fluorine. Okay, so I want to go and teach you exactly what is this hydrogen bond. So here, the X and Y could be nitrogen, oxygen, or fluorine. Okay, so the X and Y is nitrogen, oxygen, or fluorine. Now, here, nitrogen, oxygen, or fluorine, they're going to have lone pair. You guys remember lone pair? Yeah. They're going to have lone pairs. Okay. Now, what hydrogen bonding is going to happen between the lone pair and the hydrogen right here. Now, here is what I want you to pay attention to. Nitrogen, oxygen, fluorine. Are those electronegative atoms or not really? What do you think from remembering previous chapters? Oxygen, fluorine, and nitrogen, those are electronegative. Those are electronegative. Now, if you were an electronegative atom, if you have a high electronegativity, what does that mean? So oxygen, nitrogen, and fluorine, they have a high En value. If you have a high electronegativity, what that means is you're pulling the electron towards yourself. Because the way I teach En is kind of like, who's the stronger, right? That's the way to look at it. Who's the stronger? And these three guys are strong guys on the periodic table. So what that means is they are pulling the electron towards themselves. So in this bond, hydrogen has a lower En than nitrogen, oxygen, or fluorine, because that's what's going to be here. And that means is the electrons are pulling towards this way. Now, because of that, because these atoms right here, they're pulling more of the electrons, they have more of electrons, what we have here, we have a partial negative, because they have more electron than they should. And hydrogen here is that's a symbol for partial, because it's gonna have a partial positive because it has less electron than it should, because over here, nitrogen, oxygen, or fluorine are pulling it this way. So far, so good? Okay. Thanks for following me so far. Now, check this out. If this hydrogen has a partial positive, that means this hydrogen doesn't have much electron, because over here, Y, which is nitrogen, oxygen, or fluorine, are pulling it this way. What I can tell about this hydrogen is desperate for electron. This hydrogen wants electron. Well, guess what? Guess who has electron? This guy over here. So this guy has electrons to give. Hydrogen wants electron. That's a good force over there. That's a good force of attraction over there. So far, so good? Okay. So, again, this is an H bond because the hydrogen is desperate for electrons and the other guy has electron to give. That's a great attraction. Now, one thing I want you to think about, to remember for hydrogen bonding, even though we call it a hydrogen bond, is not really a bond, it's an attraction. All the intermolecular forces, they're attraction. They're not bonds, they're attraction. We're good so far? Okay. Now, before I give you an example and talk about water, I want to be very clear that to have hydrogen bonding, to be able to have hydrogen bonding, what you need to have HN, HO, and HF. So the hydrogen has to be directly attached to nitrogen, oxygen, and fluorine. Why does it have to be directly attached? Because they're electronegative atoms. They have a high En value. So then in all these three cases, hydrogen is going to be desperate for electron, so it will be attracted to the lone pair of that atom. Okay, so you have to have it. Repeat after me. HN, HO, HF. HN, HO, HF. You have to have hydrogen directly attached to nitrogen or oxygen or fluorine to be able to have hydrogen bonding. Are we good so far? Okay, beautiful. Now what I want to show you right now, and I would have to draw this out, but it's okay, we can do that. So you guys got this down? Okay, so hydrogen bonding, responsible for a lot of things. For ice being less dense than water liquid. For you being unique, because that's how DNA is held together. Now what I'm going to do, I'm actually going to draw the hydrogen bond between water molecules, okay? And you have to kind of be a little bit, I can't draw this from memory. You have to be a little patient with me. I'm going to draw this out. So be a little patient. Okay, so I'm going slow. I don't want to make a mistake. This is on camera, right? You can't make a mistake on camera. I think this is good, but I can maybe do a couple more. Sure, so that one is over there. I can do one over here. That goes here and here. Okay. Okay, so again, you can also look up hydrogen bonding in water, ice, and then you can get this picture. But I wanted to draw it out kind of like in a simplified way. So now here's what I want you to look at. So water molecule, water has OH, right? And we said NH, OH, or FH would have hydrogen bonding. NH, OH, and FH would have hydrogen bonding, okay? So water has OH. So this hydrogen, it is desperate, right? This hydrogen is desperate for electron and is going to be attracted to the lone pair of oxygen, nitrogen, or fluorine. So this oxygen has a lone pair, and then there's going to be a force between this hydrogen that is desperate for electron and this oxygen that has lone pair. So electron deficient has electron. These are all hydrogen bonding. Electron deficient has electron, hydrogen bonding. Okay, so far so good. Electron deficient has electron, hydrogen bonding. Okay, now I want you to look at this. These are beautiful hydrogen bonding. Hydrogen bondings are very nicely together. See, these are held together very nicely through hydrogen bonding. Now, these beautiful hydrogen bonds, if you look at it, they are leaving empty spaces. So when you have this hydrogen bonding, you're going to end up having a lot of pockets. You're going to end up having a lot of empty spaces. So far, so good? Okay. Now, if you are a solid, in a solid form, do you have more movement or less movement? Hopefully you're telling me solid has less movement, right? So if you're a solid, if you're in a solid form, and because you have less movement, you have all these beautiful hydrogen bonding, which means you also have all these empty spaces. So I'm going to repeat it again. In a solid form, there is less movement, right? In a solid form, things are a little bit tighter. There is less movement. Now, when you have less movement, what that means is you have all these beautiful empty spaces, right? So you have all these beautiful empty spaces and there's not much movement. So it's going to be less dense because you have all these pockets. You have all these empty spaces. So you are going to be less dense. So far, so good. Now, if you are in a liquid form, you have more movement, right? In a liquid form, you have more movement. Now, if you have more movement, then these nice hydrogen bondings are kind of moving around a little bit. You don't have as many nice empty spaces as before. So now this is going to be more dense. Okay, hopefully that makes sense. So again, liquid form, more movement. So you don't have all these, you have some of it, but not as many beautiful as hydrogen bonding with the pockets over here. So it's going to be more dense and a higher density. So that's why in a solid form, when things cannot move and we have all these pockets, we are going to be less dense. So far, so good? Okay. So this is why ice is less dense than water liquid. Now, let's do a practice problem. What do you think? Do a practice problem? Let's do a practice problem to make sure you really get hydrogen bonding down before we move on to next one. Here is a practice problem. What if I have NH3 and NH3? Can the hydrogen bond together? And what if I have CH4 and H2O? Can they hydrogen bond together? What do you think? Okay, you can pause my video to work on this a little bit and then unpause me. Now here's a hint before you pause me, don't pause me yet. To figure this out, a lot of time you have to draw the Lewis structure. Okay? You have to draw the Lewis structure. So in this case, I have NH3, okay? I have NH3. So if you remember, NH3 has a nitrogen, has a lone pair, has a hydrogen, hydrogen, hydrogen. To have hydrogen bonding, you need to have hydrogen directly bonded to nitrogen, oxygen, or fluorine. So yes, NH3 can do hydrogen bonding. Now, I said I have another NH3 nearby. I have another NH3 nearby, okay? So I'm going to have another NH3 here. How would the hydrogen bond together? How would the hydrogen bond together? Now remember, the hydrogen is electron deficient and is going to be attracted to the lone pair of the nitrogen and the other molecule, right? So yes, they could form H bonding. All right, next one, CH4. So what I'm going to do, I'm going to draw the Lewis structure for CH4, okay, and H2O. I already know that H2O has OH, so it could do a hydrogen bonding. But can CH4 do a hydrogen bonding? No, this hydrogen bonding is not going to happen. Here's why. Yeah, this water can do hydrogen bonding. It has lone pair to give, and also this hydrogen is electron deficient. But over here, CH does not do hydrogen bonding because carbon is not electronegative enough. So hydrogen is actually very happy. They're sharing the electron pretty equally. So carbon is not, it does not have a high EN value, and this bond is not very polar, right? So they're sharing the electron pretty equally. So hydrogen is happy. Hydrogen is happy, and because hydrogen is happy, and put a happy face, smiley face. Because hydrogen is happy, it is not eyeing the electrons over there. It's happy. It's not going to check out those electrons. Sounds good? Atoms are so much like human beings, as you can see. So it's pretty happy. It's not going to eye those electrons on oxygen. So these two cannot do hydrogen bonding because they both have to have OH, NH, or FH to do that. We're good so far? Okay. Nice job. So NO and F is the key to have to do hydrogen bonding. Now, look at the list. Look at the list. So we did ionic interaction, and then we did hydrogen bonding. What is the next one? What is the next one? Look at the list. Don't look at the board. Don't cheat on me. Figure it out. Dipole, dipole. Dipole, dipole. Okay? Now, we said that an ionic interaction is when you have ionic molecules, metal and a non-metal together. Hydrogen bonding, when you have HN, HO, or HF, right? Now, for dipole, dipole, you have dipole, dipole when you have covalent compounds that are polar. And I will explain to you what that means. I want to put HCl here. I want to put HCl here. Hydrochloric acid. So, if you go to lab and you have a bottle of hydrochloric acid, it's not just a few HCl molecules in there. They're going to be millions and millions of water of HCl molecule in there. Okay, so if I go to lab and I have a bottle of hydrochloric acid, what that means is in that bottle I have millions and millions of hydrochloric molecules in there. Now, how are they held together? They're held together through dipole-dipole interaction. Now, why is that? Let's check this out. So, Cl has a higher En value, is more electronegative than hydrogen. So what that means is, we just talked about it a minute ago, means the Cl is going to pull the electron toward itself, right? And what that means is, again, that means Cl is going to get a partial negative and hydrogen is going to be partial positive. I want to explain that one more time to make sure we're on the same page. So it has a higher En value, which means it's pulling the electron toward itself. So it has more electron than it should. That's why it has like a partial negative. And hydrogen has less electron than it should. That's why it has a partial positive, right? Negative means you have more electron, right? Positive means you lost electron. You have less electron. Same over here. So when I have a bottle of hydrochloric acid that has millions and millions of hydrochloric acid in there, how are they held together? So I have all these partial negative and partial positive. So do you see that attraction? Do you see that attraction? Yes, you do. This is the attraction over here. This is the attraction over here. So the attraction of partial negative and partial positive. Now, why isn't this one as strong as ionic interaction? You probably know that because when we had an ionic interaction, it was a full plus minus charges, right? It was a full plus minus charges versus here, now we have partial negative and partial positive attraction going on. Are we good so far? Okay. Now, This had dipole because HCl is a polar molecule. HCl is a polar molecule because electrons are not distributed evenly. Now, if you don't remember polarity and Lewis structure, go back to that lecture to make sure you understand it. So far, so good? Okay. Now, I also want to give you a little hint. When you're deciding if you have a covalent compound or not, we said, how do you know if you have a covalent compound? Two nonmetals together, right? Consider hydrogen as a nonmetal, and that makes your life a little bit easier. So, when you have a compound, you're deciding what type of IMF it has. If it has a metal and a nonmetal, it's going to be ionic. You draw the Lewis structure, NH, FH, or OH, you have hydrogen bonding. To know if you have dipole or not, it has to be covalent and it has to be polar. Now, covalent, when you have two nonmetals together, but what I want you to kind of think about it, consider hydrogen as a nonmetal when you're deciding you have a covalent compound or not. That makes it a little bit easier. All right, so that's a dipole between hydrochloric acid. Now, I have another practice problem for you. Here's our next problem. Bf3. I have a bottle of boron trifluoride, okay? Which means there's millions and millions of Bf3 molecules in that bottle. The question is, what type of IMF are holding boron difluoride molecules together? Okay? Bf3, two nonmetals together. Do you agree? Okay, I go two nonmetals together. That's good. And then that means I have covalent. Okay. Now, what I'm going to do, as I said before, draw the Lewis structure. Draw the Lewis structure for Bf3. Okay. This is the Lewis structure for Bf3. So far, so good. Okay. This is a Lewis structure for Bf3, and if you remember, boron is one of the exceptions that is only happy with 6 valence electron. It's not greedy. There's not 1A. Okay. So I'm asking you, what type of IMF does it have? Now let's go down the list together. We had ionic, we had H bonding, right? And then we have dipole, and then we have London dispersion. Is it ionic? It's not ionic, because to be ionic, you need a metal and a non-metal, like NaCl. You need a metal and a non-metal. So this is not ionic. So that is a no-no, okay? Is it hydrogen bonding? We don't even have hydrogen, right? No, it's not hydrogen bonding. Is it a covalent compound? It is a covalent compound because I have two nonmetals together. Now remember, to have dipole, you have to be covalent and you have to be polar. Is Bf3 polar or non-polar? Bf3 is non-polar. Bf3 is non-polar. And again, if you do remember that, for previous Chem 1A lectures, make sure you go back to those chapters. Or rewatch my polar or non-polarity video. Okay, so it's non-polar. So because it's non-polar, can it be dipole? No, because dipole, you have to be polar, right? Electrons cannot be distributed evenly. The molecule has to be polar. So my other option is London dispersion. So let's go over what is London dispersion. Now, I probably don't even need to tell you what is London dispersion. So dipole is when you have a covalent compound, which is the two nonmetals together that are polar. Now, what do you think London dispersion is based on this? It has to be a covalent compound that is non-polar. A covalent compound that is non-polar. It has to be a covalent compound that is non-polar. So, last one is a London dispersion. So, how do you know you have a London dispersion? It's a covalent compound. So, if you have two nonmetals together, and don't forget, count hydrogen as a nonmetal for me. But then when you draw it out, the molecule has to be non-polar. And we already did an example, and I want to use that example since we already know that well, to show you how this happens, how this happens. So Bf3 we said is covalent compound, and we said Bf3 is non-polar, right? Now, if you remember what non-polar is, so I have boron here, I have fluorine, and I have fluorine. The electrons are distributed evenly. That's what it means to be a non-polar. So this is a non-polar molecule. The electrons are distributed evenly because I have electrons on every side of the molecules, right? So electrons are distributed evenly. I have a little bit of molecule there, I have a little bit of molecule there, I have a little bit of molecule there, right? Every side of this molecule has a little bit of electron. I have electrons, electrons are distributed evenly. Every part of the molecule has some electrons, okay? Now, remember this, that molecules are moving. There is a motion at room temperature, right? So there is a motion the constant motion at room temperature. Molecules have a constant motion at room temperature, okay? Now, because of that, because they have a constant motion at room temperature, once in a while, they are rearranged a little bit. And in this case, they will be rearranged to this. So, I will explain this in a second. Let me draw it out first. And I will explain this in a second, okay? All right, so here's my Bf3, okay? I have boron, fluorine. Fluorine has a higher EN value, so it's pulling the electron this way, pulling the electrons this way, pulling the electrons this way, okay? So every part of the molecule has some electrons. That's what it means to be non-polar. Now, molecules are moving. There's a constant movement at room temperature. So molecules are moving constantly at room temperature. Now, as they're moving constantly at room temperature, sometimes they get rearranged. So now I have boron here and I have fluorine on the other end. Now, when this happens, remember, fluorine has a high EN value. So now I'm going to have a partial negative here and partial positive there. Partial positive, partial negative. Again, this is what it is most of the time. But all of these there's a constant motion at room temperature. They're moving rapidly at room temperature. And because of that, once in a while, they have this kind of arrangement. Once in a while, they're going to be rearranged into this kind of arrangement. Boron is here, fluorine is over there. So now, once in a while, temporarily, when they're in this shape, now fluorine has a higher EN value. So now this is going to have a partial negative, this is going to have a partial positive. And you could find another Bf3 molecules that also has the same arrangement that has a partial negative and partial positive. Again, why is this N negative? Because these are the fluorine. Fluorine has a higher EN value. So, what does that mean? What you're going to have? You are going to have an attraction between partial positive and partial negative. And this is temporary. This is a temporary. Because again, there's constant movement, and once in a while, this happens. It's a temporary dipole. It's a temporary dipole. And they also call it induced dipole. They also call it induced dipole. Okay? Why is that? Because this polarity, this partial positive and partial negative, this is what they call dipole, right? When one atom is pulling the electrons one side, and you have this partial negative, partial positive, that's what it means by dipole, to remind you of previous lectures. So once you have this temporary dipole, then they are going to be attracted to each other. Now, why is this the weakest IMF? Is the weakest IMF because it's temporary, right? It's not a permanent. It's once in a while, as they're moving, they're going to have an induced dipole. They're going to have an induced dipole. Are we good so far? Yeah? Okay, all right, so let's repeat this one more time. So here I have Bf3, right? Here I have Bf3. I just put a circle to kind of see. I have boron over here. This is a nucleus, and I have the electrons going around it, okay? Now, when I have this going on here, the electrons are distributed pretty evenly around the molecule. Okay? Now we said electrons are constantly moving and they're orbiting around the nucleus. Now sometimes by chance, temporarily, they gather on one side of the molecule. And when that happens, then they're gonna, you see that? So once in a while, what happens is they're going to gather on one side of the molecule. Temporarily, they're going to create this dipole. Now, they could also find another one who has this temporary dipole, and then there's going to be an attraction there. Okay? Now again, like I said, this is temporary, by chance, once in a while. This is why this is the weakest intermolecular forces. Yeah? Okay. So far so good? Okay. And again, this is like a force over here between the partial negative and partial positive. I can do this. All right. Let's do a practice problem. Let's do a practice problem. Alright, so now we've gone over all the intermolecular forces. And again, one time reminder, London dispersion is the weakest one because it temporarily happens, right? Temporarily, the molecules are going to gather on one side of the molecule, and the electrons are going to gather on one side of the molecule, and you're going to have this induced dipole, they call it, right? Because again, it's not as high it is, but by chance, once in a while, as they're moving around rapidly at room temperature, this could happen. And then they're going to have a partial negative or positive, and they can be attracted to another Bf3 with the same position. All right. Now, Cl2 versus H2. What I want you to figure out, which one has a higher intermolecular forces? Which one has a higher IMF? Okay, so we need to figure out what type of IMF each one has. Do you agree? So Cl2, what type of IMF do you think it has? Cl2, I have two nonmetals together, right? Two nonmetals together. And if I draw Cl2, is that polar or non-polar? That's non-polar, right? Electrons are distributed evenly. Both have the same En value. Okay. H2 over here. And remember what I mentioned. I said when you're doing these things, it's going to save you a lot of time. Don't forget to consider hydrogen as a non-metal. Okay. So I have, this is also a non-metal. I'm going to consider it. And it's also non-polar. Covalent non-polar, covalent non-polar. Okay. So they both have London dispersion, right? They both are going to have London dispersion. So they both have London dispersion. If they both have London dispersion, what does that mean? Which one is going to have a higher intermolecular forces? What do you think? If you had to pick one. Okay, so now here's how you would do this. Here's how you would do this. If you have two molecules and they both have London dispersion, which is the case here, the heavier molecules would have a higher intermolecular forces. By a heavier one, the other way to look at it, the one that has more electron, the one that has a more total number of electrons is going to have a higher IMF. Why is that? Because remember, London dispersion is temporary and by chance. If you have more electrons, if you have a higher molecular weight, you have a higher chance of temporarily having created induced dipole. So far, so good? Okay. So, if you have cases that they both have London dispersion, the way you do this, the one that has a higher molecular weight, or the other way to look at it, the one that has more electron, more total number of electron, is going to have a higher IMF. Because again, remember that. And the other way to look at it is the one that has a more electron than the one that is heavier, right? So the electrons are far away from the nucleus, and it's easier for the electrons to get rearranged, right? Because here's the nucleus, here the electron. If the electron is far away from the nucleus, it's not really feeling the nucleus plus charge, then they can play around more and they can rearrange to have an induced dipole. This is why the larger molecule, the one that has more electron, would have a higher dipole. Which one would that be? That would be this one. This one is going to have a higher intermolecular forces. Yeah? Okay, nice job. I think this is enough for right now. So we've gone over ionic, which is the strongest IMF, then hydrogen bonding, which is HN, OH, or FH, then dipole-dipole, which is covalent polar, Ionic dispersion, which is covalent non-polar. And what we're going to do next time, we're just going to do nothing but a lot of practice problem to show you how to decide what type of IMF they have. And why do we care about IMF? We care about IMF because we can predict physical properties. All right, nice job, guys. I'll see you guys next time.